about first order Pde, but before doing this, let's just start really from our elementary differential equation course and try to make connections between ordinary differential equations and partial differential equations of the first order. Right, so how we move from ODE to PDEs. I assume that everyone has taken at least undergraduate course of elementary differential equations, and you know that the first order ODE looks like this. So we have dy dx equals some function of x and y, and we assume here that x is an independent variable and y is dependent variable. What does it mean to solve this equation? To solve this equation means to find such a y as a function of x, so to find such a function psi of x such that when we substitute this function into our equation, we have an identity, at least in a certain domain where x and y are changing. And there is existence and uniqueness theorem, so when it is possible to solve this equation, so if function f of xy, so the right hand side of our equation, is continuous, and also if partial derivative df dy is continuous in some domain D, then for any point x sub 0, y sub 0 in this domain exists unique integral curve passing through that point. So, and here I made a picture, so this is our domain D. We have on our axis we have x and y, and we have a bunch of integral curves, and if we fix a certain point x naught, y naught, we have just exactly one point passing through this point, exactly one integral curve passing through this point. And very often, so we have a bunch of curves, and just to specify a certain curve, we usually give what we call initial conditions. So we say that when x equals x sub 0, y equals y sub 0, right? So that's how we can choose a certain curve among integral curves. And we can think of y sub 0 as a constant, and if we change y sub 0, we will be, by say keeping the same x sub 0, we will be jumping between integral curves, moving from one integral curve to another integral curve. So, and in this way we have one parameter family, right? So the solution of equation depends on, if we have first order ODE, solution depends on one constant, and this constant can be defined from initial conditions. So now let's move from one first order ODE to a system of first order ODEs. So suppose we have n equations, and suppose we still have x as independent variable, and y1, y2, yn, they are functions, unknown functions of x. And now in the right hand side we have functions that involve x, our independent variable, and all of the unknown functions. So we have this system. Let's give it number 2. And what do we call a solution to this system? So it would be functions, if we can find function y1, y2, yn as function of x, such that when we substitute them back to our system we get identities, then we call this set of functions solution to our system. And you probably remember from the course of ODE that systems of n first order ODE ODEs is equivalent to 1/nth order ODE. And you probably remember that this general solution depends on n constants. To find these constants, we can add initial conditions. So if we pick a certain point x sub 0, then we can define initial conditions by giving a certain value to a corresponding function y. And again, by changing these initial conditions, we will be changing our solution. So solution is defined up to n constants, and I can write this fact as y each y with subindex I, where I runs from 1 to n, is a function of x and n constants. And then, if we assume that conditions of existence and uniqueness theorem, which is similar to the theorem we just reviewed for one ODE, if they are satisfied, then we're able to solve these equations for C's, right, with respect to C's. Now this system is written as resolved in terms of y, so y is a function of something, and then we can solve it for C's, suppose, if conditions are satisfied, and then we will get each constant Ci as a function phi of x, y1, y2, and yn. And these functions, phi's, they called first integrals of the system 2, or just integrals. And we can note that, of course, when we are talking about functions phi, we assume that we're not talking about just something that is identically a constant. So it's the general non-constant functions, but they are constant if we substitute here solutions. Obviously, it follows from here. If we plug here for y1, y2, yn, if we plug solutions to the system, then we will get a constant. And if we plug for each of them solutions that get a constant, then if we consider an arbitrary function of this phis or phi's, then we also will get a constant. So we can write that arbitrary function of all phis is a constant. So I put here circle that if we will not take all n functions, but only a few of them, say k, which is less than n, we still will get a constant. And it makes sense also because sometimes how we are finding these functions, phi or phi, we're not finding them simultaneously. We're finding them one by one, and if we found at least few of them, then our problem becomes easy. If we can find all of them, then we have completely integrable system. So before showing how the system of equations is related to system of ODEs is related to a PDE, let me do a few more comments. So first let's look at this system again, right? And then let's look at every specific equations. So each equation is dy dx equals f, right? Each of them. And then but f's are different. But now if, for instance, we divide each equation by f and multiply by dx, right? Then we will have dy over f, and that would be for I will be changing here, but every equation will have dx in the right hand side, the same dx. So we can then set them equal to each other. So let's go here, the side which had dx, let's make a fraction, so let's divide it by 1. It's not necessary, but just to keep a structure. And then we will have equals dy1 over f equals dy2 over f2, and so on. And we can write it even in more symmetric form. Because what do I mean by more symmetric? So here we have some functions f, here we just have 1. If we multiply everything by a certain function, right, then we will have some functions everywhere. And suppose we did this, multiply by a function, and then we also can change notations just for the sake of having it more symmetric. So from old notations where we had x and then the rest were y's, now we can call them all x, and then instead of x and n y's, we will have just n plus 1 variables, since we had n plus 1 variables here. And then in new variables, new notations, we will have dx1 over f1 equals dx2 over f2, and so on. And then now we will have dxn over fn, and the last one will be dx plus 1 over f1. And here our functions f everywhere, they are functions of all variables, right? From they depend on x1, x2, and up to xn plus 1. And then here, just let's have an assumption that all functions f capital are continuous, and partial derivatives with respect to all of the variables, all of them, x1, x2, xn plus 1, are continuous as well in some domain. And also let's assume that, for instance, the last one, fn plus 1, is non-zero at some point. If we fix the point in our domain, assume that fn plus 1 specific function is not zero. Then by continuity, since all f's are continuous, this specific f also will not be equal to 0 in some neighborhood of that point. So then each equation can be written as dxi over dxn plus 1, and here we'll have fi over fn plus 1. So that way we will have in the denominator, we will have only this function fn plus 1. So then it would be enough to assume that this function is non-zero at a point, and then the conditions of uniqueness theorem will be applied, satisfied. So we can comment that we have to talk about special points only if all functions fj equals to 0. So this is our main equation. I gave it number 3. So this is our equation that we jumped from 2, the system 2 to 3. And if we're talking about 3, expression of, in such form, any function of all of the x1, x2, xn that is constant is called integral. And if we can find n integrals, so n functions depending on our variables x1, xn plus 1, then these integrals are called independent integrals. These equations can be resolved for n of xk, right? So here we have n plus 1 variables. If we can say appoint one of them as independent and resolved for the rest of n of them, then such integrals are called independent integrals. And if we do so, then we will get n functions of one variable with n arbitrary constants. So the situations with solution to this equation, equation 3, will be the same as situation with general solution to our system of ODEs 2, right? The general solution had an arbitrary constant. Okay, so here I copied again our system 3, our system written in this symmetric form with respect to every variable x1, xn plus 1, right? So f, capital F, again, functions of all variables. And now let's look at the system and assume back that, let's say, x1 is an independent variable. It doesn't matter which one, but for definiteness, let's assume that x1 is independent. And then it means that x2, x3, and n plus 1, if we want to find the solution, or if we found the solution, they are functions of x1, right? So if we find this x1, x2 is function of x1, x3 is function of x1, and xm, so that plus 1 is function of x1, we have a solution. And now let's assume that phi is our integral, right? Phi, we just talked about integrals of the system of equations, so let's phi be this integral. And then what happens if we plug for x2, x3, and the rest of them our solutions? So instead of x2, we'll plug function of that depends on x1. Instead of each of them, we'll plug functions of x1. So the whole expression will have only x1. But the question is, does it have x plus 1? Because what must happen? The whole thing must be equal to constant. So if we do this, then x1 also must be eliminated, right? So otherwise we will not get a constant. So then here we will not have x1. And what does that mean? So it means that this function phi will not depend on x1, and if we want to differentiate with respect to x1, let's take total derivative with respect to x1. This total derivative must be 0. So how do we compute derivative with respect to x1? So derivative with respect to first variable, then first variable with respect to x1, derivative with respect to second variable with respect to x1, right? So we write it here, d phi dx1, of course dx1 with respect to dx1 is 1, and d phi partial derivative dx2, here we have ordinary derivative, right, because of these functions of one variable dx1, and so on. So then we will have this equation, and since this whole expression doesn't depend on x1, we will get here 0. And then we can slightly modify this equation. Let's multiply everything by the differential. So here it's just multiplication. By differential dx1, then we will have d phi partial derivative dx1 times dx1 plus d phi dx2, and so on. D phi dx n plus 1 dx plus 1 equals to 0. And then now look at number 3 back. Right, what we can see from number 3, that our differentials for a certain s or certain I, right, are proportional to fs because of this structure. So then we can replace then differential with functions f. Equation will stay the same, so what we will have, f1 times d phi dx1 plus f2 times d phi dx2 plus so on, plus fn plus 1 d phi dn plus 1, and let's call this equation number 4, and now you can see that now we have a first order PDE, right? We have equation with partial derivatives of the first order. Here f1, f2, fn plus 1, we can think of them as coefficients of this differential, and coefficients, we know that coefficients are functions, and we can think of this equation as equation for function phi, for known function phi. And basically what we just discussed we can summarize as a theorem that if we started from here, right? So if function phi of x1 xn plus 1 equals c, if this expression is integral of 3 of this system, then function phi itself is a solution to this PDE 4. And it's possible to show that it's vice versa, so function that is solution to this PDE will give us, when set to constant, will give us integral of system 3. So we have shown that our PDE 4 and our system of ODE 3 are equivalent.